So that's all. So there we go. We can make that out. Perfect. Okay, so first of all, we're going to talk about what comes before that, which is just a very basic construction, which you can already use to do a bunch of stuff, and which secret sharing is just going to be a generalization of this using polynomials. So a basic problem is one of communication. So you have like Alice wants to communicate with Bob, and he has some message M that he wants to send to Bob. And he doesn't want Eve, who is seeing, let's say, so you have two communication channels. Let's say Eve is seeing one of them. We don't know which one, but one of them, not both. And you want to communicate privately so that Eve doesn't learn anything about the message and Bob does, right? So one way you could go about this is if you are sending messages. So F2 here is just binary bits, so they're just zeros and ones with the operation that if you do 1 plus 1 is going to be 0, 0 plus 1 is 1, and 1 plus 0 is 0. So if you do this type of construction, so you just send a random bit in one of the channels, and in the other one, you add them up and send them, Bob will be able to decode. He just needs to subtract what goes on the top from the bottom, and he gets the message. But Eve will not learn anything about the message at all. Obviously, if she observed the top one, she's just looking at a random bit. But the important thing is that if she looks at the bottom one, it's also a random bit, because if you knew M, you would know R. And R is just random, so it's sort of equivalent, knowing one or the other. So this is just a basic way of having just secure communication if you have two channels and Eve is not able to see everything that's going on. And this is called a one-time pad, because you can only use this R once, and you're padding your message. And if you want to send a bunch of bits, you would just do this for each bit that you're doing, right? And please interrupt me if there's any questions at any moment or any comments or so. Now, this idea can be used for a bunch of problems. Just to give some examples. So one of them is if you want to store, so instead of transmitting information, let's say you want to store information in some server, and you want to store it in a way that you can only, you want to access it later in the future, you don't want the servers to know what you're storing. You can do the same thing, and maybe the main idea here is that you can actually view this as if you were if Alice was Bob, but in the future. And the communication channels are the servers where you're storing stuff. So you could see that also as some form of communication channel. And so you can use this for what's called distributed storage, which is used in a bunch of applications. You could use the same type of construction for a bit of, I'm not going to go too much into details here, but for a bit more complicated problem, which is called private information retrieval, where you want to download something. So imagine you want to download some video from YouTube, but you don't want YouTube to know which video you downloaded. And here, what you do, what this whole diagram is just saying is, so you have both servers, they have a data set, so you can imagine those are the videos or so. Imagine them as these bits. And what you do is, EI is the video that you want. It's just the one in the place that you want and zeros everywhere else. And what you do is something which is just a inner product with the database. It's just multiplying your vector with the database. But the idea here, that doesn't matter too much. The idea is that if you do the same construction where you just hide what you're asking with the randomness, you also get a random query, essentially. The servers are not able to know what you were asking for. So this is, yes.
How's that any different from what Tor does? You know, the Tor network?
Yes. So the Tor is a bit of a different setting, right? It's more of a, so there are a lot of differences right there. So one of them is that the Tor it works by like jumping around, like how do you say, like you have a bunch of these nodes in the network, and once you go within the node, you don't know exactly what's going on inside as long as you don't control a bunch of them. but then you have these like outside and inside nodes that go to the network outside. So in Tor, you have to be careful that when you have things being downloaded. So for example, if you write an email in Tor, everyone's going to see what you're writing, the content of your. They're not going to know that it came from you, but if you write your name there, they're going to know that it's you. So it's a bit of a different thing there. But you could try to do something similar for maybe downloading some type of object, and you're going to have the same type of issue of if people control too many of the let's say what would be the servers here, they could also break what you're doing. So I mean there are some similarities. Tor is also more it's computational security based. So whereas this is statistical security, here if you do not control both of the servers, I can guarantee that you learn nothing at all because it's just completely statistical. In the Tor that I know of, they use cryptographic protocols, which are not completely statistical. So there are differences. But yeah, but you could probably use something like that with some caveats to do similar things. And you can also, these type of problems, you can do them for secure computation, which is a similar problem where Alice now, she wants to compute something out of the servers. She has like some vector and she wants to do some multiplication and get something back. And these things could be part of like, nowadays machine learning is a very hot topic. And machine learning, a lot of it is doing a bunch of these matrix multiplications. And you might want to be outsourcing this or using information from the outside, but you don't want people outside to know what you're doing exactly. And you can do the same type of construction with these one-time pad type things. Now, all of that was essentially with these two servers, send a random thing and send what you want with the random and then the code. But obviously in many applications, you have more complicated settings, right? You might want to have multiple servers, you might want to break up the things that you're doing. And then how do we do that, right? And one way of doing that is, which I'm going to show here, is through something called secret sharing, which is just to generalize this idea. And to just get to it, the idea was that what we were doing before, this idea of sending a point and a point plus something random is going to be as if it's going to be a scheme that came from like a line, and the generalization of this is just using polynomials. So we're going to see how that goes. So a simple example of secret sharing is a problem of the following type. So you can imagine that you have a bank that has a safe, and this safe should only be open in the presence of 3 managers out of 5. So you have 5 managers, and you need 3 of them to open the safe. So to be able to open whatever, each one has their own little key, let's say, and you need 3 keys to be able to open. If you have less than that, they shouldn't be able to open it. If you have more, they should. And the idea is, how do you distribute? So you can imagine, like, you could give passwords, but how do you do this thing where you have like one password and it's distributed in a way where if 3 of them come together, they're able to find out the password, but any less, they're not able at all to find out the password. So the intuitive idea behind this and why you would use polynomials is that if you have a first degree polynomial, just a line is determined by 2 points, right? If you have a second degree polynomial, you can determine it uniquely by 3 points. And then the idea is that if you take a second degree polynomial, so you need 3 points to determine it, and you were to share 5 of these points with the managers, then any 3 of them could retrieve the polynomial. And if you get less of them, the idea is that there would be maybe some infinite amount of polynomials that pass through 2 points, and so they wouldn't be able to retrieve the secret, right? And the secret is some evaluation at 0, let's say. So intuitively, this sort of makes sense. It's not gonna work directly, and we'll see why. And the reason that it's not going to work, so when we were doing secret sharing, no, so we weren't doing the one-time pad. So what was the property of the key in the one-time pad? was that it's uniform, right? It's completely random. Uniform random is the same probability for everything, right? If you try to do the same thing here, or with this argument with the polynomials over the real numbers, you don't have a uniform distribution over the real numbers.
That would be a lot less secure than just generating an encryption key like AES 256 and then just dividing it by 3 among managers, right? Because I would bet that polynomial has like a more consistent behavior where you can guess points than an AES.
So if you do it, so the thing is the following. So with real numbers, this doesn't work because you can't have a uniform distribution. If you have a uniform distribution, which is what we're going to work with, the type of security that you get is perfect security. It's not breakable even with infinite computational power, whereas AES is breakable with infinite computational power. The assumption here, AES is strong because you don't care about like collusions. Like you're okay with everyone seeing what everyone has, and then it's a computational guarantee. This is a statistical guarantee. Here, as long as you have less than 3 managers, it's just statistically impossible to get it if you can have the uniformity of the random keys. And we'll get to that. Now, the point is that the construction that we were doing before, you're not able to, so you have a uniform distribution there, and if you just do this with polynomials over real numbers, you're not able to do that, which is why we need to work with some structure where we can have uniformity, and we're going to see it's going to be a finite field. So a field is just what you expect the real numbers, the properties that the real numbers satisfy, essentially. That you have some addition, some multiplication, you have something which is a 0, that when you add, you get the same thing. You have something that is a 1, which is when you multiply, you get the same thing. And maybe out of these, one of the most important properties here, or at least that distinguishes it with many things, is the multiplicative inverse, the existence that for every number you have an inverse. So, for example, if you take the integers, they're not a field because not everyone has an inverse, right? So 5, there's no integer that you multiply 5 and you get 1. That's why you sort of do the rationals. So the rationals are a field. That's sort of their whole thing. However, they're also an infinite field. The point is that we would like to be able to work with a finite field because we want to do the same algebra that we do essentially with real numbers, but we want to do it in a place where we could uniformly take things with some uniform distribution. So if we have a field that's finite so that we can take a uniform distribution sample from it, but it still operates all of these nice properties, we can essentially treat it in some way as if they were real numbers, but having these nice properties. And one way you can go about doing this is with something called modern arithmetic. So this is just many of you are familiar with. You do it every day when you look at the clock. So when you do so it's the arithmetic that happens in the clocks, right? So when you do like 12 plus 5, it gives you 17, which is the same as 5 because you just go around on the clock. Or in other words, you just any number that I give you, if you were to divide it by 12 and see what was the remainder, it would be what the time is, right? So 1800 hours is 6 p.m. because 18 mod 12 is 6, right? Now, we saw that the first field we were using, F2, is just the clock with 2 guys, which is just what happens when you work with bits. And it was this type of operation that I was telling you, and one could go and check and see that this satisfies all the field operations. It's very easy to check that you have multiplicative inverse, so everyone that's different than 0 has an inverse, because there's only one guy different than 0, and he is his own inverse. So 1 is quite easy. If you go, so you can do with bits, you can do with more than just bits, and we'll see why we're actually gonna need to be, we're not gonna be able to do things just with bits. This one is Z3, so the clock with 3 guys, he's also a field, because everyone has an inverse. So the inverse of 1 is just 1. The inverse of 2 is just 2 itself, because 2 times 2 is 4, which When you divide by 3, it gives you a remainder of 1, and so on. But then you take someone like Z4, it's not a field. And the reason for it is that 2 does not have an inverse. So there's no one that you multiply by 2 that just gives you 1. And the reason for that, one way to see it, is that when you take multiples of 2, which is just repeated addition of 2 here, you always end up at 0 and sort of coming back. So in general, if you end up at 0 at some moment in the clock, it's not going to work out because you're never going to be able to go to the number 1. And this will happen exactly when your number divides that number of the clock. So in this case, it's because 2 divides 4. So the only way for you to guarantee that you will have a clock such that no one, when you add repeatedly, ends up at the top, at the 0 of the clock, is by taking a prime number. So ZP, the clock with a prime number of I don't know how to call the numbers in the clock, but the prime number of positions is going to be a field, and you can test that it's going to have all those nice properties. And like we said, it's going to have an inverse for everyone. And so from now on, this is essentially where we'll be working on. We'll be working ZP, and we'll see. We saw that it's because we want things to be like a field. We want to have finite so that we can take uniform, and we'll see now why we need them to also, how do you say, to be more than just 2. So back to secret sharing. The idea is that, so you could just take that idea that we were talking about that secondary polynomial, but instead of doing it over the real numbers, you're going to do it over Z7 or F7, which is just mod 7 integers. Now, the reason for that is because we're going to have to, so if we look at the steps, we're going to take uniformly 2 elements of F7. So this is what's going to give us the security. And we're going to define this polynomial here, which is just the secret. So remember that the P of 0 was the secret. The secret was just on the x equal to 0 axis. And we have these 2 random keys that help us in hiding it for all the other values. Now, since we have 5 managers, we're going to need to have each manager is going to receive one of the evaluations. So P of 1, P of 2, P of 3, up to P of 5. With the P of 0 that is the secret, you need to have at least 6 elements in your space. With binary, you're not able to do that. You only have 2 elements in space. You would only be able to send P of 1 to someone. And that's why you need the field to be larger than just a field with 2 elements. So there's no way around that in some sense. You need to work with a larger field. Now, if you do that, what's going to happen is that if each manager is receiving one of these y's, another way of looking at it, apart from how we saw in the picture, is, let's say, the linear algebra way of looking at it, is that it's equivalent to this system here, where 3 managers get to see 3 of the equations. And we know that with 3 equations and 3 variables, in this case, you'll be able to solve. But the point is that this is a special system that with 2 equations, you're not able to remove any of the randomness at all. So here, and because of the uniformity assumption, if you do not get 3 equations, you just do not have enough information statistically to, it's going to be uniform distribution over all the possibilities. So in that sense, this is better than any type of computational cryptographic method. Than just AES is good for other reasons, for other type of applications and reasons, but for a secret sharing thing, that's the strength of this, right? So any questions here?
So like you said something about like the clock when it has 4, the two things it will not work. It won't be like a field.
Yes.
Because your 2 doesn't have like a
yes, an inverse.
So if you do this with like, let's say you want to have it so that like there are 4 managers, or is there any like issue with your final solution such in a way that like if there are like 4 managers, or if there's like 4 passcodes that it won't work?
No, it'll work. So what will happen is you just you're just gonna pick a large field, and your secret,
Yeah.
it's gonna be an element of the field. So what's gonna happen is, it's not gonna be about the number of messages, but it's that the secret, like, it might be inefficient if, let's say, you just wanna hide one bit, it's a 0 or 1. But here, the secret is an element of F7. So there's a bunch of possibilities. So let's say that, and you should be, in principle, storing any of the possibilities. So it's sort of like, so you're gonna probably like pad your 0, 1 with extra stuff. So you're just gonna be inefficient. It'll still work, but you're just gonna be like solving in a space that's bigger than where your answer needs to live. So it's not gonna be an issue with the amount of people that are, the field is, you need the field to be big because you give different evaluations to people, but that does not relate with the applicability of the scheme for any amount of people. Like, it's just a matter of, if you want to hide just 0 or 1, you can still do it here. There's this inefficiency that's. Moreover, secret sharing, there are schemes that are done like over Z4 and stuff like that. They're just more complicated because then you're not able to do linear algebra. So the whole point is that with fields, you can do linear algebra. Z4 is still a ring, so you have something like the theory of modules, which is like linear algebra over rings. You can still do stuff there, but things are less well behaved. So you have a bunch of other difficulties that can come up, but it is possible to do these things, and sometimes for efficiency reasons, you might want to. Okay, so the way that it looks in general, and let me not lose track of time because I get excited with the topic. So the way that it looks in general is that you're going to have some, let's say for now, a prime field, and you have your secret, and you have your number of shareholders, and you have a certain minimum amount of them that you need. What you do is for each person that you need, you're gonna put like a random key, and then your degree of the polynomial that you're gonna work on is just the degree of this minimum, because you need t points to be able to determine this polynomial. So in general, that's just how it looks. So you get a polynomial of degree t minus 1 because you need t evaluations to retrieve it completely, and that just gives you a scheme where you need more than t people to be able to get what you want, and with less than that, you're not able to do anything. And that's just what the general secret sharing construction looks like. And again, you can then apply this to a bunch of stuff. These are just some small examples in the same way. So that was like the manager problem, but here you could, the same type of communication problem we were talking about before, you can now allow that Eve observes more than just one path between your communication network, right? Same thing for like distributed storage, and this is used a lot for distributed storage. So you essentially have n servers, you give each server an evaluation of a polynomial. And then the idea is that you need, if you do this construction that we talked about, you need a certain amount of them to be able to answer. So here you could make it so that even if the servers talk to each other, you need at most, you can't have all of them talking to each other, but if you guarantee that at least one of them is a server that doesn't know about the other ones, or that in some sense, you don't need to know which one, but that they're not all talking to each other, you're just good to go. So they use a lot because it's easier for you to select. So in the communications, sometimes it's a bit harder because sometimes when people intercept communication, they know who you are and who the other person is. Whereas here, it's like I could use Dropbox and then go and do like a different account with a different service or something like that. And these services don't need to necessarily know who I am and where these things are coming from. So this is easier to enforce. And you can then do private information retrieval also. I'm not going to get into the details, but it's essentially the same type of thing, but you just hide your query and so on. And again, you can do the same idea for the distributed computation stuff. So you hide computations that you want. So the idea here is just to show that this secret sharing construction can be generalized to a bunch of interesting problems. I'll give a final little extension of this, and then I'll give a fun puzzle, but you only get the puzzle if you stay till the end. So the extension here is we're gonna also, so we're gonna use the polynomials now to do not only security, but see how we can get error correction and all these things sort of for free in the middle of this. So an MVT ramp scheme. So before, how did it work? You had this parameter T of how many managers you wanted to be able to access the safe, and less than that, they weren't able to. So there was like a sharp threshold. It was like, if you have one manager, there's nothing, he doesn't learn anything, 2 doesn't learn anything, 3 doesn't learn anything, until T, he learns everything. And then from there on, you just learn everything. This is more of a less sharp transition, where essentially up to T, you don't learn anything. And then from T to B, you start to learn slowly. You learn a little bit each time, until at some moment you just learn everything. And this, it generalizes, and it's going to be useful because you can use it for error correction. We'll see how. So then the idea is that before you had just one secret, and all the rest were random keys. Now what you do is these ones that are partially revealed, you have a bunch of informations in the coefficients, and then at some point you have random keys. So if you have t minus 1 random keys, you know that if t minus 1 or less people see, they're not going to be able to learn anything. And then after they get one more, they're going to start to learn linear combinations of this. They're not going to learn the precise thing, they're going to learn linear combinations of this, but it's some information. So they're slowly going to learn information about it until they retrieve all of the points, and then they can just retrieve everything. So this is just a generalized version of that. And this I'll just show through examples, like if we just go over the parameters, what happens. So this one here, you have 3, and this could be used for storage or anything. I just took this as an example so that we can measure the stuff. So here, Alice and Bob, let's say you have 3 paths, and with parameters b equal to 3, t equal to 3, what you do is what we saw before. You just have one message, and you have 2 keys. And what this means is that Eve can see, if Eve sees any 2, but not all 3, she's not going to learn anything. And that's it. Bob will learn what he needs to learn. Now, what is the rate of this? And I think this is wrong. This is like 1/3. It should be 1/3. Right? So the rate here, to send one message, I have to send 3 things. So it should be 1/3. So I'm sort of paying like this 3 times things to get one thing. And the maximum observation, sort of like the security is this, and there's no error correction, because we're going to see that we're going to have error corrections in the next one. There's no error corrections or any of that stuff going on here. Now, you could also then add more information to what you're sending, right? And now what happens is that when you do this, now, since you only have one key, you only protect fully against an Eve that observed 1. So you have less security than before, but you get a better rate than before, because now you're sending 2 messages through 3 transmissions. So it's a 2/3 rate. You still get none of the other stuff. Now, if you lower the polynomial side, the degree of the polynomial, now look what happens. Since you have one key, you protect against one Eve. You're sending 3 evaluations. So you're sending 3 things to get one thing. So this is the 1/3, protecting against one Eve. But now there's a new thing going on since you lowered the degree of the polynomial. Since you sent 3 evaluations of the polynomial, and this is a polynomial of degree 1, you only need 2 of them, which means that if one of them is lost, you're able to correct and get the correct answer. So if one of them, you just lose them, you're going to be able to correct. And so this corrects against an erasure. An erasure is when you know that something was lost, like you got like something failed or you didn't get anything. That's an erasure. An error is when something is like swapped. You're not able to correct an error because if you get an error, if you get 3 things and one of them is wrong, you're not going to know what was happening. Like if you do like you could think of like, oh, maybe wanting to do like some type of majority, but there's no majority here to actually go for. You don't know if this one was wrong or that one was wrong, so this one doesn't correct for that. Now, you could also take the higher degree polynomial and just remove all the security, and you just get a communication rate of 1. This might not seem too interesting, but there is a caveat. If you are able to enforce that these guys are uniformly distributed, and there are ways to do that, to convert it, you do get a weaker version of security called individual security, which is Eve only learns about combinations but doesn't learn about individual messages. But it's just, so there is, even this is useful for something. It's again, you can also do something like this, where you get no security, but you get erasures being corrected and a very good rate. So here, no, this is not 2/3. This is wrong. All the calculations are wrong. Forget about the communication rate. Communication rate here is just 1. Oh no, it's 2/3 because you're using 2 channels. Yeah, it's correct. Don't believe me, believe the slide. It's 2/3, yes. You have this scheme, which is the stand constant. This is called the repetition code. And this one has a bad rate, but you're even able to correct against errors by majority voting. If you get 3 things and one of them is wrong, you know that 2 of them are right. So just look at the 2 that are right. So you can correct 1 error, and so on. And these, so if you continue to do these things and you remove the security part, you actually get something called Reed-Solomon codes, which are quite good codes actually, and have these type of. So it's the exact same thing that we did, but removing the random keys that were used for security. So maybe the big picture here is that if you just take the polynomial and decide how you want to put the info, so you have 3 things to choose. How you distribute the information, so if you're putting information or random keys to get security or not, and the degrees of the polynomials, which is essentially deciding how many evaluations you send, you're able to play around with the rate, the security, the error correction capabilities, and you can sort of exchange these things one for another. So you can get more security at the cost of rate by removing one of these things. So you can play around with all of these things. And it's just a cool construction that just comes very easily from polynomials, essentially. And the puzzle, you made it. So fun puzzle. So let's say Bob has a polynomial with positive coefficients, strictly positive. No, none of them are 0. And Alice only knows that. She knows that he has a polynomial with strictly positive coefficients. But she does not know, for example, the degree of the polynomial. So she doesn't know the degree of the polynomial. It could be degree 10 to the 50. She doesn't. Now, Alice can ask Bob for evaluations. So she's allowed to say, oh, Bob, what is P of 1? What is P of 7? What is P of 8? Right? What is the smallest amount of questions that she should ask to determine exactly what polynomial it is? So, for example, if she knew the degree of the polynomial, as we saw through this whole talk, if she asked for n+1 evaluations, she could just retrieve it. But here, she doesn't even know the degree of the polynomial. It could be 10 to the 50. So I leave you with the puzzle. And that's it.
Questions?
Does your puzzle have a definite answer?
Yes.
Okay.
Oh. So okay, so I like the question. So if the x here is only integers, there's one answer. If you allow real numbers here, it's a different answer. You can, and obviously you can do better with the reals than with the other because like a stealing strategy, right? Just do the other. Yeah.
One question.
Just to clarify, the answer to that puzzle is independent of n.
Yeah, should be. Yeah. And the answer to the 2 questions. So if I show the answer to the 2 questions, generally to an engineer, the integer one, they're okay with it. the real one, they hate it. And then, but I can show that they're essentially the same thing. We can actually make the real one actually work in practice also. It's not just like some. Whatever, and then they more or less accept it once. So, yeah.
Is it the reals, the rationals?
So
Is there a different answer for the rationals?
no, for when I say real, rationals is the same
So
as
it's the positive.
integers. Okay.
Other questions?
So the security comes from the polynomial going on forever, because technically you can guess points forever, right?
What do you mean on the scheme?
Yeah,
of the security
that
schemes?
security comes from, if you don't know there's 3 managers, it'll take you forever to guess.
No, it doesn't. No, it doesn't come from that. It comes from the because it's only finite amount. So it comes in the. So think of it like this: when we were doing the first, we were sending, like if you do just a line. So if you do just a line, your secret is here. And you have an evaluation here. What you're doing is you're using the polynomial s plus r x.
Yeah.
And so one manager is just storing, let's say, f of 1, right? But you were doing it over bits, right? That's why one of them was storing like the secret, and the other one was sorry, the secret plus r, and the other one was just storing r, right? Over 1 bit. So these S and R, and 0. R was uniformly chosen. Okay. So if you make a table of the possibilities, what's going to happen is, let's say that S is 0. Half of the time, R is going to be 0, half the time it's going to be 1. And then on half of the time, this here is just going to be 0 or 1. And if it was 1, the same thing, half the time it's going to be 0 or 1. So you have access to all the information. But if you're not able to see both of these, you're not able to know what it is. It's going to be 50-50 chance for each one. And that's the same thing that's going to happen with the other construction over the finite field. You're going to have a uniform distribution for the symbols. If you go and do a table of all the possibilities, if you observe less than the threshold, you're going to see that you're going to get a uniform distribution on your guess with the information that you have. It's going to be equal chances of being everything independent of what the original message is.
So you can't just guess points.
I mean, you can guess, but your chance of getting it right is the same as just randomly guessing.
It would seem to me that a computer can guess points far faster than it can.
But it's not about you can always guess.
Yeah.
But the point is, okay, so you guessed 7. So is it correct? You have the point is all of them are going to have the uniform distribution, right?
Yeah.
Or let's say, okay, if you had access to an oracle that could confirm if you got the guess right, then then for any scheme you can always guess. Now the best scheme over a list, a finite list, if you have an oracle that can tell you got it right or wrong, and now let's say that you try to do a strategy, the best strategy is just gonna, on average, find it on half the size of the list because it's just uniform, right?
Yeah.
This is gonna achieve that, which is just the best thing.
So it isn't actually possible to check if your answer is right if you randomly guess.
So that depends on the application, right? So that depends if in the application you have access to some oracle or something, right? But then what I can prove is the following. And so this can be proved for the secret sharing stuff also, which is because if you have access to that, sort of what's happening is like you have some type of side information that you're trying to use to verify which one you think it is, right? So what you can show through the secret sharing thing is that whatever you gain from the secret sharing observation is not helping you given your side information, which means that you're just as good as if you had not seen anything and you were just trying to guess. Like the problem is just completely equivalent to me showing you the stuff is the same as if I hadn't shown you anything and you were just going to try to guess it. Like if you hadn't even seen the transmission, it's the same. The transmission doesn't help. You can show, so statistically you showed that they're like, how do you say, independent. So the random variables for what's happening in the transmission that you're seeing are independent.
So there's a way to answer this question, independent of the degree of the polynomial. It must depend on, you can't just guess random things. It must, if I take a guess, then my next guess must depend on what you tell me.
That's great. So when you know the degree, when you know the degree, and you ask for n+1, this is a static algorithm where you just ask n+1 questions, and you're good, and you just solve it. So yes, there's such a thing as a dynamic, which is you first ask, you look at the answer, and based on the answer, you then do another question. So yes, this should be solved via a dynamic algorithm. So you should ask, look at what you got, and maybe think about it in some way.
Right, because it's clear that you can't do this with a static algorithm. Right.
So that's gonna be, for the real numbers, it's gonna be a bit tricky.
All right,
But for the integer one, yes.
right.
For the real one, it's gonna be, that statement is gonna be tricky.
So I noticed that most of the research you cite is fairly old. It's like from the 1980s.
Yes.
So I haven't seen much of this like in my life. Is
Yeah,
there a reason as to why this isn't like widely applied?
it is applied. Secret sharing is used, so, and so even for the AES and stuff, for
Yeah.
key, for storage of keys and stuff like that, it's used a lot. And in a lot of protocols, it's used as an underlying protocol. So you see like a big protocol,
Yeah.
and these things are used like internally as components of things. Yeah, so they use these kind of things. But it just has been like brought into, so think of it like this, as time has gone and newer things come, they construct on top of these things.
Yeah.
And the new thing is just gonna get whatever name it gets. But yeah, so private information retrieval, and you're gonna have the whatever paper I showed you there, and you could get their schemes just by doing secret sharing and doing some stuff. The private information retrieval actually, so you can get the schemes by doing secret sharing, but the best schemes, you have to do an extra trick on top of that. So you do like secret sharing, and then you do like a combinatorial trick on top of it, and you get what's the best schemes, but it's like an underlying scheme of what's being done. But yeah, Shannon is 50s. Secret sharing is actually, so this is sort of reverse. Secret sharing is 79. And Reed Solomon is before by quite a lot, by 60. So like almost 20 years before. And the connection between them wasn't like, this is the first paper that does the connection between them. It's in 81. So they sort of even went in sort of like parallel ways. Like you had this error correction literature, and then secret sharing appears out of nowhere, and they start using it for stuff. And then later they make this connection that these two things are sort of related in some way. And nowadays you have even stronger connections. So there are like things that you do in coding theory that relate to secret sharing results.
Other questions? Okay, let's thank our speaker. Thanks. Yeah, do more for us. Very sure.
I'm more positive.